So problem one, writing a function rule, says you can estimate the temperature by counting the number of chirps of the snowy tree cricket. The outdoor temperature is about 40 degrees more than 1/4 of the number of chirps the cricket makes in 1 minute. So obviously you have to be able to time for a minute. What is the function rule that represents this situation? So if we take a look here, first off we know again the temperature is 40 degrees more than 1/4 of the number of chirps in 1 minute. So let T represent number of, or the temperature rather, N is the number of chirps in a minute. So it's important there that we define a variable. So we're going to write a function. Now something here to think about as we're doing this is the fact that, there we go, let me change my pen color, is the fact that negative numbers, whether or not they make sense here, right? Because you can't have negative chirps. You can't somehow suck chirps back in or whatever. So that doesn't make any sense. And then we have to also think about what is the minimum temperature that this is applicable for. Obviously, if you're 0 chirps, right, 40 degrees and below, you're going to have, there's going to be your degrees is the idea there. So, alrighty, so again, we have to think the number of chirps, so 1/4 of those, right, plus that 40-degree barrier that we talked about, that is equal to the temperature. Now, again, if that was something you struggle with, you got to stop and ask yourself, what do the words mean? We hear things like more than, right? So obviously that means we're going to add in this case. 1/4 of, so, right? And then obviously, again, T. So don't forget to define your variables first. Alrighty, so for your first got it, says a landfill has 50,000 tons of waste in it. Each month it accumulates an average of 420 more tons of waste. What is a function rule that represents the total amount of waste after M months? So again, we have to define a variable, right? So let M equal number of months, and W is the total waste. That's garbage, that sort of thing. I didn't really write that variable. There we go. W-A-S-T-E. Okay, so we have to ask ourselves again, where does it start? Well, there's that threshold, that 50,000. And every month we have 420 more. So again, you can see that we're going to write here 50,000 plus the 420 times M is the total amount of waste. Now this is one of those functions where you could actually kind of go back in time, right? So it went back 1 month. You're going to actually subtract 420 here. 2 months, you're going to really be subtracting 840. So you kind of can use a time machine to really figure out, when did they open it? If I were to ask you that question. Anything past that, though, obviously, you can't go into negative waste. But in this one, you can kind of use negative numbers. Okay, so second example says a concert seating plan is shown below. Reserved seating is sold out. So we're going to consider that to be a constant. That's this section right here. There's 10 times 12 number of seats. That's $25 each. Total revenue from ticket sales would depend on the number of general seating tickets sold rather. Write a function rule to represent the situation. What is the maximum possible total revenue? So some of the things here, like that last question, indicates, hey, I can't go over the amount of seats here, right? Not possible. So down here, we take a look at this part. We got to figure out, it says it's sold out every time. So that's a constant no matter what. So we have 10 rows times 12 seats. So that's 120 seats right here. And we're going to write that in with a pen so we can keep track of that. So right here, there's 120 seats. But, again, multiply that times $25 a ticket, and that's going to give us our, I believe, what, 3,000? Yep, that's going to give us our constant of $3,000. So that's a set. It's added right on top of it. General seating up here, we have 30 times 16, and so that's 480 seats, right? And then times $10 a seat, so that's going to be $4,800 total possible. We can't go over that, right? So that's that whole maximum possible total revenue. All right, so when it comes to writing the function here, we're going to let R as the total revenue, N is the number of general seating tickets, right? Notice we're not including the reserved seats because that's part of our constant. So what we're going to write down here is this function. We're going to have $10 times number of general seating tickets sold. And then that $3,000, that's the sold out reserve. That's going to equal R, the total revenue. So that's our function rule. Again, the most you can make, right? So if I sold out all of these seats here, the most I can make is that $4,800 plus the $3,000, or $7,800. That's the most I can make. Alrighty, got it too. A kennel charges $15 per day to board dogs. Upon arriving, each dog must have a flea bath that costs $12. That's a one-time charge, by the way. It's not every day. It's when you walk in that door, kind of like we talked about getting in the taxi cab, those kind of things, or walking in the door to reserve the hall or whatever. Write a function rule for the total cost n of days of boarding plus a bath. How much does 10 days cost? So we're going to first off start off with defining a variable. So n equals number of days, right? And we're going to say c equals total cost. Okay, so what we're looking for here is we have that $12 just to walk, that's the bath, right? That's kind of like the walk in the door cost, plus $15 each day times the number of days is going to be our total cost, C. Now to figure out, again, how much does a 10-day stay cost, right? So you're going to plug a 10 in there, so you're going to have 12 plus 15 times 10 equals C. And we're going to find that's equal to $162. And we had that right down here. So, second part of that, does a 5-day stay cost half as much as a 10-day stay? Sounds good, right? But that's not really what happens because we can't forget that we've got this whole $12 flat rate charge. So that can offset. It's not exactly half, so it's going to be a little bit more than half. So because this doesn't get halved just because you stay half as many days. Okay, so our third example. A little bit of geometry fun here. Write a function rule for the area of a rectangle whose length is 5 feet more than its width. What is the area of the rectangle when its width is 9 feet? So we all know that if you look over here, the formula for the area of a rectangle is length times width, as evidenced by my beautiful picture here. But again, we're not doing two variable equations. We're not ready for that. We'll do systems later. So we have to replace the L with the representation of length as a function of the width. In other words, W plus 5, right? So it's 5. It says it's 5 longer. So again, our formula really is W times W plus 5. Now, so we've been asked then, so define the area. So W times W plus 5, that's, here we are, down here, there we go. That is the total area. And now, in order to get this, so we'll move from here to here. Let's write that down for us. We know that our formula for area is W times W plus 5. You're going to use distributive property, right? And that'll take you down to area equals W squared plus 5. Now here you notice we come into that whole squared thing. And we said if something's squared, cubed, whatever, that it's definitely nonlinear. Okay? So this is, again, that nonlinear function idea. And it asks us, so when the length then is, or the width rather, is 9, what's the area? So we plug that 9 in, right? So right here for W squared, so 9 squared is 81. And then, oops, you know what I forgot to write in there? I forgot to write in, there we go, the 5W. So we go back here again and we plug in our 9, so 9 squared, that's coming from here. 5 times 9 coming from here. Add them together and get 126. And again, don't forget to label that's feet squared. Okay, so write a function rule for the area of a triangle whose height is 4 inches more than twice the length of its base. What is the area of the triangle when the length of the base is 16 inches? So that's a lot, right? So it sounds like a lot of work. Like, oh my gosh, what do I do there? So let's start simple. We know that the area of a triangle is base and height, right? So the formula is area of a triangle is 1/2 base times height. So it's known. You should know that. So now the thing is, get back to this idea of what, the twice 4 inches more and all that stuff, right? So let's draw another little picture here, and we're going to kind of translate what that means. So here's my area still, and here's my base. It says that the height is 4 inches more than twice the base. So twice the base plus 4 inches. So my formula really becomes this. Area is 1/2, right, base times height, which is base times 2b plus 4. It's a 4, I promise. All right. And again, we kind of have to build on each other because we're multiplying the b here, this base, times the entirety of the height. So a little distributive property fun comes into play here. So we're going to have area is 1/2 of the base times the height. So that's 2b squared plus 4b. Half of that, I'm going to need some room. I'm going to have to move up here to the top here, I think. So we distribute the area is half of that, so half of 2 is 1, so that's really just b squared plus 2b. So there's our actual formula we're going to end up with, right? That's the one you should have written. And again, you need to pause, rewind, go back and take a look at why I did that, what all we did there. So, alrighty, so it says, what is the area of the triangle when the length of the base is 16 inches? So a little bit of plug and chug here, right? So we have area is 16 squared plus 2 times 16, right? There you go. So that should give us area is 288 inches squared because it's area. So that's an 8 right there, I promise. So 208 inches squared. As for the second part of that, let's go ahead and go to the next slide for that. Okay, so a little bit of plug and chug fun here. Now, obviously, it doesn't make sense to have a negative base, so we start with 0. Plugging in 0 is just going to give me 0. So we have the point 0, 0 over here. Plugging in 2, we get 8, so 2, 8 right there. Then plugging in 4, we get 24. So again, this is just plug and chug stuff, right? So square the 4, add 8, that's up here. So we can see very quickly this is nonlinear, and again, we've discussed this idea that if you have the squareds in there, cubed, whatever, it is not linear. It grows like that. So there you go. There's your got it. By the way, there is no vocab in this section, so just this video after you're done with your reading got it for tonight.